Pleased to welcome Alexis Arnaudon from Imperial College.
Thank you for inviting me for giving this talk. I'm not sure I want to thank you for the schedule because I don't know if you noticed that I'm the first French speaker of this morning session speaking about landmarks and statistics. So, okay, I'm the last one, I think. So this is joint work with Darryl, Holm and Stefan, Sommer and some other people as well. And so this is the part one, and Stefan was going to give the part two after lunch. So this talk is more like a pre-lunch entertainment. so I wanted to ask to do like Laurent ask a question in the title and try to answer it. So my answer to this question is use fluid dynamics. Maybe some of you know this already, right? So you know how to do. You know how to deform images using fluid dynamics. I want to show you how to shape images as well. So on how to do both together, right? So let's start from fluid. So what is fluid is this picture I took from video from YouTube, which shows you two big vortices, so one rotating clockwise and anti-clockwise, and so they collide and they do things, right? And fluid dynamics tells you that this is equation. This is not correct, but if you believe, it should be an equation of this style that does this dynamics, right? Actually, you have cascading, so it's not quite correct, but suppose it's correct. So then you say, okay, what geometry? What do you mean by this equation, right? So let's have a look. You do the usual thing, right? You say you have a fluid domain, reference points. You have a map that maps reference positions to the new one. For every time they compute v, you compute little x, which is Eulerian position. So it's just evaluating your flow at position capital X. And then you have this Eulerian velocity. You know all that, right? It's just recalling. So then you say, let's take a Lagrangian just kinetic energy, and then you can compute the equation of motions for your fluids or rigid body in this case, right? Easy. Important point here is this equation. How to relate the speed of the fluid at position X with respect to the Lagrangian particle capital X, right? You need to invert this phi and plug it in. Okay, so then you say, let's have a look at this Lagrangian. Then you say, okay, change of variables from this capital X to little x, and then actually it's the same norm, so we can say the same equation. So this L is in fact L of little v. Okay, and then you do the usual variational calculus, and then you get this equation, Euler point carré. So now the important, and then so you solve this equation for v, and then you will need to find phi using this relation here. So the important point here is that this equation is actually the fundamental equation that you need. So you say I have phi, I define v in this way, and then I want to compute the equations for v. So if I want to modify somehow my theory, I need to modify this equation and then recompute this one. So this one is the fundamental piece of fluid dynamics, right? In this sense. So at star, what is at star is the usual one. It's L2 dual to commutators, and then you take brackets, you integrate by parts, and you get at star. So you go back to the usual fluid equations if you do all the algebra correctly, right? So if you interpret fluid dynamics in this sense, in this abstract setting, you can play with what at star is, you can play with what Lagrangian is, and you can play with what do you mean by this equation and how you can perturb this equation, right? So I'm going to do several things. Okay. So let's go back into this big picture. So here you see you have the main point to see is at different scales, right? You have these big blobs and a lot of small filaments doing crazy stuff. So you don't want to stimulate the whole thing with like a very fine scale. You just want to do something like I want to capture the dynamics of those guys by getting rid of those small scales, right? Something like this, which is something reasonable to do, right? So you say you do this technique. So by the way, this was Arnold in the 60s. So I'm jumping 20 years after, and this is Darryl in the 90s, which is assume that your trajectory is x, so a smooth trajectory plus some perturbations. So in this it's quite clear, right? You see this one is moving, but then it's perturbed by those guys. So it's kind of almost x, but it's x plus little noisy xc with a length scale alpha. Then you have this. You can say, okay, the speed is actually the speed at not x, but x plus little c. You want to, in the Lagrangian you have this v squared, so you have average here is average over the noise guy here. So you just expand and you say alpha is small, and then you could take the average because this is isotropic noise, and then you get down to a new Lagrangian, which is the usual one plus some gradient term. So it's Sobolev norm. And you compute the equation and you get this, the EPDF equation, right? So in this setting, the EPDF equation is telling you don't just follow trajectories along those lines, but follow many of them and take the average. So try to probe what is a little bit outside of the mean trajectory, right? So it's getting a bit more non-local by trying to capture the small dynamics that influences you nearby. Analysis. So it's, I think in this context, a bit different than usual image matching. It's a different flavor. I think it's interesting to see the differences. So, okay, you have this equation, which is also the same from Euler-Poincaré and add star and everything, right? I just changed the Lagrangian here. Didn't do much. Then you say, okay, actually, I want to do more. I don't want to solve the full PD. I want to solve just the position for those two blobs, right? So you do landmarks. So you say, okay, you have the V, you have the M, which is just convolution with this kernel, and then you plug in Q's and P's, and then you derive the equation of motions. And the structure you preserve is the Hamiltonian structure of your equations, right? It becomes the Hamiltonian, which is just kinetic energy with interactions with the kernel. So you see now the alpha term is really trying to how to say? Yeah. So how do those guys interact in reality? I mean, those guys is moving a little bit the fluid parcels here, this one as well, this one as well, and then interacts through this process, right? So by averaging, you're saying, I want to, for the motion of this point, I want to take into account the motion of that point, and so on. And if you do this correctly, then you can have interactions of those 2 points without knowing exactly what's happening in between, right? So that's the idea of this method. So if you solve this for just those two positions, it's good for sometimes, and then maybe the dynamics is getting away from. I mean, those little things have too much interactions, and then you lose your precision of approximations. So then part 2, images, you know, right? So this is like a large deformation. I like this picture; it's quite nice. So here the idea is. I don't care about what's happening inside, so I want to average this, and then I just want to care about the scale from, right? And here's the same as ventricule. I don't care about all the stuff happening around it. I just want to take it to compute the dynamics of those boundaries. So I put landmarks on the boundaries, right? The same as fluid. I don't care about the little things that happens between the vortices. So the same, you actually solve boundary problems, right? The usual one. So matching D to H, for example, this is from Collinscotter's paper. So you see that here you actually minimize this action, so you have a Euler-Poincaré equation somehow. That's coming in. Okay. So now the next question is if you have many images, how do you, like we said this morning, how do you take mean, and what do you mean by, how do you characterize the fact that those guys are slightly different in space, right? So that would, in the context of fluid dynamics, it would correspond to say, if I run this simulation again, I would have the similar picture but slightly different. So this guy would be a little bit different positions because those noisy turbulent flow will interact differently with the vortices and give you a different realization of your fluid dynamics, right? So if you just average in a continuous setting, you don't capture the fact that if you run again a simulation, you get something a bit different. It's like predicting the hurricane Irma. You have this nice mean trajectory where you have this big, you don't know where it's going to go after time. Sometimes you need to get statistics of actually how precise my approximation is for the position of this guy, and then you can say it's plus minus some position, right? So you want to introduce noise that captures this, and it sort of captures what you remove by averaging. So you're averaging, you remove a lot of dimensionality by having just solving a set of ODEs, but you still want to capture the randomness of your initial simulations by some kind of noise, right? And here in images, it's just I want to tell you those guys are actually different realizations of stochastic evolution of images. And if I have one model with different noise realizations, I can get to this one, this one, this one, this one. So what I want to do now is to try to find what noise give me all those possible realizations, right? So you can't get everywhere. You can get to some extent to near the mean image if you want. So how to do this? Then I'm going to do just landmarks here, but you can do this for all the structures you want, right? So you say, okay, let's rewrite the problem in this way. Let's try to minimize the Lagrangian, right, to find minimum finite energy. But I want my landmarks Qi to follow the vector field V, right, the usual one. And this is Lagrange multiplier, right? Now I'll say, okay, it follows V, but not quite. I'm making mistakes by following the trajectory I should follow if I were exactly deterministic and exactly following my mean trajectory, right? So I add this term, which is telling me if you are at Qi, if Qi is at X, then you have some noise sigma, right? And this dW, if you don't know stochastic process, this is just a dt. If you think of discrete case, this is just dt but random dt, if you want. So you don't know it's a dt taken into a normal distribution, if you want. And circle here means you need to integrate this in a nice way so you can do computations. So you actually say on my image I have a bunch of function sigma which would be kernels. So I wrote them here. So kind of kernel sigma at position delta L with some parameters. So you have the amplitude here. This is just the form of the kernel with radius RL, so some kind of Gaussian blob. And if my landmarks goes through this Gaussian blob, it will feel the noise. And if it goes away, it doesn't feel the noise, right?
Maybe you could mention V5.
Yeah, sorry, yeah. So this, okay, let me go step, yeah. I think I should have written the slide differently. So you start from this, and then you compute, you can just take three variations, you compute and you get this Hamilton equations, where you can actually say, let's call P dot this guy phi, because H is actually P dot VQ, right? So let's call P dot sigma Q phi, and then I can write it as Hamiltonian times dt plus Hamiltonian times this noisy dW, right?
Yeah.
So
Here the noise is X.
So this W, when you do simulations, you pick up random numbers, and those should be the same random numbers in both. For each L, so I have a set of L, K random process, and for each one I have different sigma.
Well, and then the noise is varying with the path.
Yeah.
Okay, amplitude is varying
So
with the path.
if you want the picture, if I'm on the line, I take a bunch of sigmas. So this is sigma 1, sigma 2, and when my landmark goes here, it feels sigma 1 and then feels sigma 2, and so on. Right. Is it? And I can take as many as I want. I can take as many sigma as I want. And what you want to do, if you take a basis function of R2 of your image, and you sum up to infinity, you get a white noise in space and time, if you want. But you don't want to do this, right?
When you do to compute the stochastic equation, when you optimize Lagrange and you fix the noise and you do the optimization.
Yeah. So this is for, everything depends on the noise you choose. So that's why this is like, if you solve this with a fixed noise, it's going to be, you're going to get one image. And if you run again with different noise, you get this image and so on. So it's really like, Okay, so this is it's nice because then if you do it, so remember this equation is the one that I said it's a fundamental piece, right? It's a reconstruction equation. So I'm actually perturbing. I think I have this next slide. Okay, I should have done this differently. So in the general case, what you do is you say this phi at the beginning is just reconstruction from the vector field U plus some noise. And this works for any data structure, any group, any Lagrangian. So you don't need a Laplace, which is exactly the same term, but you replace U is dH dV, and here sigma is the phi dV, right? If you want. So in the case of landmarks, everything is nicer. You can see it better. Okay, so let's go back. So now this is a weird equation. If you look at it in terms of physics, usually we want to do this, right? You want to say I have a stochastic force acting on my momentum, right? So this is kind of Langevin equation. But what we have is two noise with the same W in both Q and P, with this weird form, right? So it's kind of additive in the Q and coupling P and gradient of sigma and gradient of the noise. So if you have a lot of large momentum and a lot of gradient of sigma, then you are coupling and then you modify P. So it's a weird thing. The other difference is like sigma depends on Q, so it's kind of fixed Eulerian noise amplitude. Whereas here is sigma of I is just a number which tells you this landmark I has some forcing on it that is random, right? So it's quite a different approach for those two. So what's like, okay, let's compare numerically. Let's compare what's the difference between those two approaches, right? So you take a circle here is 100 landmarks on the circle, and you want to match it to this dash black circle. So it's very like simplest possible matching, right? So you take, if you do just additive noise, so if you just do this one, you have the magenta curve, right? Some noise. It's not exactly the circle, it's circle plus noise, right? Now if you fix, so now my sigma was this quotient patch, and if I put them in those positions here, and then I say, okay, I'll put parameters such that it's roughly constant on the same constant on the space than this number. So it's roughly the same noise. Then I get similar random shape, right? But now the trick is I have very noisy trajectory here. Why? Because I had noise in the Q equation, so the trajectory itself is noisy. Whereas before, if you have just noise in the P, the Q is quite smooth. You don't really see the noise in the Q, right? Now you say, okay, let's play with parameters and let's do the following. Let's increase the resolution. So let's have 200 landmarks, and by this I also reduce alpha by a half to have a convergence to some curve, right? And when you do this, you see that because for the magenta you have one noise per landmark, then you have more and more wiggly line because the spatial correlation of the noise is smaller and smaller, right? But for this case, you get exactly the same kind of shape, right? From here to here, you see it's roughly the same randomness. Now you say, okay, let's fix the resolution, but add more different noise points. So by this, I mean I change the spatial correlation of the noise in my Eulerian setting, and I can recover the same wiggly line. Right. Now if I were to actually change, from this case, if I were to change the alpha, so the length scale of the approximation, then I would smooth both curves if you want. So if in tweak parameters, you can get different regimes and different meaning of noise. Right? One thing, I mean, you can say, okay, it's very, yeah. No, you can say, okay, it's very stochastic here, and it's weird, and it's not very well posed, it's too noisy, and so on. But when you do matching, you don't actually care about what's happening between time 0 and time 1, right? This doesn't have any meaning. This time doesn't have any meaning in imaging. Right? So why not having noisy trajectories? What you care about is just the final one and the initial one, right? What happens between time 0 and 1? Okay. Something. Okay, so okay, it's the slide before. You can do this for images and so on. Okay, so now the next point is to, so my model here is just everything is, you know everything except the sigma, right? You don't know what sigma is in your application, so you want to find sigma. You want to find the noise amplitude. So sorry for the slide. You want to find sigma such that when you run different matching, you get all these different pictures, right? So what's the sigma underlying this? So sigma would be finding the template of those different images somehow. That's a different way of estimating template from noise. If you want. Okay, so what you do is you write down, you stick with landmark, so it's finite dimensional. You write down the Fokker-Planck equation. So you say, I want to find the probability of my system being at position Q, momentum P at time T, right? You compute, and then you get this nice form, which is, this is just a canonical bracket like this. So basically, think of this as one derivative on P, like this, right? So G here will be P, and this guy is twice the bracket, so it's two derivatives on P. So this is really advection term and diffusion terms, Laplacian and gradient, if you know. Which makes sense because this is a noisy part, phi is the noise, and the noise is exactly doing diffusion around your mean trajectory. Right? So you call this L star, okay, if you want L star. And then you say, okay, I don't want to, so this is, if you have like n landmarks, this would be a PDE on for n dimensions. Because you have x, y, and p and q, so if n is 1000, you have 4000 dimensions PDE, so you don't want to solve the full thing, right? And in real life, you don't have enough data to actually infer anything from this high dimensional PDE, so you want to reduce dimensions quite a lot. So what you do, you say, okay, I just care about the mean path, so I compute the average of qi, so alpha is just coordinate x, y in your image, and I is landmark I, so you just say, I integrate over all my phase space PQ, Q against the probability measure for at time t. So this is the average of my landmark position. Then you want to compute also how I deviate from the mean path, right? This is an important part. So this is error bar near the position qi. So it's just, in general, it's just q for landmark I, landmark j at alpha and beta coordinates, and you integrate here. And then you want to say, okay, I want to compute dynamical equation for those two quantities. I don't want to solve the full PD here, I just want to solve a set of ODEs, and here I have 2n ODEs, and here I have 2n squared ODEs. But it's much better than having this big PD, right? So how do you do this? It's simple, you just take time derivative, you say, okay, but I know what time derivative is. It's time derivative of p, which is L star p, right? Time derivative of p is this guy, L star is this big operator. And then actually L star means it's a dual of L, so you put on the left and you apply L on Q. And this, what this means is just a mean, the average value of this LQ. You know L, you know Q, you can compute LQ explicitly. And I think it's here, right? And you have average of this guy and average of this guy. So now you say, okay, but what is this? So H is P, P is the kernel. So this guy is P times the kernel, which is nonlinear function of P and Q. And so average of products is not product of averages, right? So you can't close this system. You cannot express. This is, you need to take derivative of this guy if you want to compute, to close it. So to say, okay, let's say QP, for example, the mean of QP is the mean of the product of the means plus some perturbations. And this is a guy that is, if those guys are correlated, that this is non-zero. Then if you have triple products, you can expand its product of means plus all the terms that are like, if you take one and then delta 2, you see what I do here. Plus delta 3, right? And then you say, oh, okay, delta 3 is 0. I'll just neglect delta 3. So I neglect triple correlations. You could take delta 3 and then compute other terms, right? So you want to compute the equations for Q and delta 2 for any pairs instead of this guy. And you expand all the terms, you expand in this way, and then you kill all the higher order corrections. If you want them, you can compute, but you need to sweat. So you do this, you compute DDT of this delta 2, and you get 3 different terms. So, okay, this is quite small, but you see it's difference between the average of the mean, the average of the product and the product of averages. And if you, so then you do another trick, you say, okay, but what can I do with this? You say, okay, let's approximate it by just putting the average inside, which is, usually this is wrong, but you have some correction terms which happens to be quite small in practice, so I mean, you can justify this more or less. And the same for the kernel, you can just say, oh, the average goes inside the kernel. Because otherwise you can't, I mean, you can do tricks if you want, but I tried, but it doesn't give much. Because the important part is not in these averages, it's in this coupling between the Q's, the noise, and so on. So here you see you have delta 2 QP, here you have delta 2 QQ. So okay, you say you just care about this guy, but actually you need to compute the correlations between QP and PP and QQ, right? So you say, okay, let's compute. And then you say correlation of PP, you expand, you do this, the same, and then you compute. Don't be scared. And then you can get do numerics. So you use Cyano to implement all these things, right? It's easy. And then you can do numerics. Okay. So what do? You start with this kind of ellipse with 5 landmarks. You fix a bunch of grid with sigmas, which are, like those sigmas are just bump functions here. So when the landmark goes here, it feels this noise, and if 2 landmarks goes nearby this one, they feel the same noise, so they shake the same, right? And then you say, okay, let's fix alpha equals is very small, so you have no interactions. And then you see the final, so the ellipse here means the final variance, so it's a QQ correlation in terms of x and y, right? So this would be like the error bar for the final position of your landmarks, right? So if you start here, at each point you can draw this ellipse and you would go along this path, right? The more noise you feel, the more error you make. So then the comparison here is just if you have more interactions between landmarks, you kind of have the more similar final variance. I don't know if you see, like the blue ones, like this one is very different from other ones, but the red ones are pretty much all the same. So because you interact with a landmark, you sort of you increase the correlation of the noise somehow. Then you say, okay, let's compare this to Monte Carlo simulation. So I can just run forward a lot of stochastic landmarks, and then compute the density. So this would be the exact solution of the Fokker-Planck, of the PDE, but by Monte Carlo simulations. And then you can compare the two, and it's not too bad. I mean, you lose a bit, but it's not too bad for the approximation of the final variance. Of course, you need to have small noise and so on, right? Then you say, okay, let's have a look at something a bit weird. So if you have remember this is a Gaussian kernel, so if you have a large Gaussian kernel, it's pretty much 0.5. So this guy is like very flat. So you can solve this by hand. I think I didn't do, but you can solve it by hand. It's just a Gaussian, right? It's just an isotropic diffusion. So this would be just a Gaussian blob, and you can compare with numerics with Monte Carlo. It's exactly the same. Now if you have this very steep, so this is just a small blob of noise, when you go near it, you have large gradient of sigma. And remember in the equation was p dot gradient of sigma. So when you have large momentum and large gradient of sigma, you have a lot of interactions, weird interactions, which makes the final distribution quite non-Gaussian. And you see, you capture quite well, but you don't capture the skewness of this distribution. And to capture the skewness, you need QQQ delta 3 interactions, which are the skewness, right? So to actually capture this well, you need to have to compute a lot more equations. But in practice, you never expect to have such a weird configuration, right? Usually you have some kind of very nice noise. But even in extreme cases, you can still capture part of the variance. Then you say, okay, I observe some variability in my data. So I have many images which should be the same, but have slightly different shapes. And then I want to find what would be the noise that corresponds to this variability in my images. So you say, okay, I have a set of observed positions for my landmarks, which are slightly different. I can compute the mean of them, I can compute the variance of them, and then I can run this fixed sigma, a fixed initial momentum. I can run solve this equation and compare the final mean and the final variance, and then build this cost and then minimize this one. So I want to find the noise such that you match quite well the final position and final variance. So somehow this is quite decoupled. So this one is solved just by finding the initial momentum, the usual shooting method, right? And this one is a new one, which is finding the noise which gives you the final variance at the end of the matching. So if you do this, you do always simple case, so one landmark. So the black crosses are the initial noise I put. Then I run forward a bunch of landmarks, and I compute estimated variance. So it's a very easy thing. And then which is a black line. And then I say to the algorithm, trying to find what the noise should be to get this black line, right? And here it finds it quite well. If you do gradient descent, it doesn't work that well. So yeah, if you want to do gradient descent, you need to compute derivative of this, right? So you better use Tiano to compute derivatives, or PyTorch or something like this, right? Because these guys are these massive equations I wrote before. So even if you do gradient descent, it doesn't capture. So the signal here is very strong on the trajectory of the landmarks for the noise, but it's not very strong outside, so you don't actually capture the noise here. Whereas if you do genetic algorithm, which is some kind of global minimization algorithm, then you can find a lot more, much better precision. So gradient descent doesn't work because this guy is crazy. It's very difficult to minimize. So in practice. So how this works? This is just you sample your phase space randomly, and then you have some rules for evolving the different points, and then it sort of cools down to the minimum of your C. But if you do gradient descent, you get stuck to some local minimum, and then it's very difficult to get out. If you want. Then you can do like several landmarks. So you use the same case as before. You have 5 landmarks, and you match them to these 5 landmarks. If you do gradient descent, you don't really capture anything. If you do numerical gradient, you can actually find very precisely, even if they are quite far away, you can find very precisely all the noise amplitude. Which is, I was quite surprised. If you do like, you can really get, if you run this for a long time, you can really get very high precision for this example. So then, okay, so let's take some corpus callosum images, right? You have lots of landmarks. So this gray, you see this gray scale here, is the average of, I don't know, 50 different corpus, I think. And then the black circles is just average computing from those 50 different images. And then I put some noise, so the red cross now has the noise fields. I put some of them here by hand, and then I try to find what value they should be to be able to match. So the blue one are the estimated one from my set of sigmas, and then you see you can capture part of the, not everything, but part of it. And if you put more sigma, then it's more difficult to compute. But you can get better. If you put 1 sigma per landmark, you can actually, I think you can get quite a precise match. But still, with a few sigma, you can get the basic variability of your. So here, so what I did here is to encode the variability of my corpus into a bunch of 10 sigma, 10 noise fields. If you want.
So, Alexis, this is an estimate of uncertainty, right?
Yeah. So this is wrong because you don't actually care about the parameterization of the curve, which here is quite noise. I mean, you need to be careful with parameterizations, right? It doesn't mean the noise in this direction doesn't mean much. It's just how you put the landmarks on the corpus, right?
Yeah, but the data you had, okay, for this landmark, you start from what?
Yeah, you start from something like, something like this. Something like this.
Yeah, because this landmark, in fact, we don't really know.
Yeah, so it's very just to try.
Yeah.
It doesn't make sense really to do this because you don't know the x. Maybe you can reparameterize or do something. Yeah, but if you have some meaningful landmarks in x, y, then you can. So you should do this with curves, which would make more sense. Yeah. But this is like computing. This is like it's not very difficult. It's like a few hours on a normal computer. Okay, so it's quite fun to put noise and see what you can do with it, and how to infer the noise from your data. And this is we just did the preliminary work on like, does it work in principle? Then what can you do with it? So you can do curves, surfaces, everything. So the trick is, if you have infinite dimensions, and the Fokker-Planck and all this stuff I talked about is, what do you mean by this? And you need to discretize somehow and do tricks. You can think about doing image matching, which makes sense because you have noise, you don't want to match exactly your final position, right? And then Stefan is going to talk about different ways of estimating the noise. You don't have to do Fokker-Planck. You can do more the different techniques. And you can do metamorphosis as well, and you can play with this if you want. And you can try to find real applications for estimating the noise if you want. Okay, so for the paper, this one is the one that I wrote for the noise in fluids, and then we wrote those couple of papers explaining what I said today. Okay, that's it. Thank you.
Questions, Alan?
Yeah, okay, so I was wondering about this, the fact that, okay, now in that model, when you generate trajectory, you get something which is right.
Mm-hmm.
In fact, you could do and okay, I'm just reacting on that because, okay, what the kind of thing we were trying to do with François Xavier is just to avoid to have this, because if we want to have this longitudinal trajectory, you want it to be smooth. But I think you can. You cannot do the same just by saying that instead of having something in a brain motion, okay, something which is white in time to have something which is correlated. And just derive this?
Yeah, but I mean,
You will get something which is smooth, no?
It's what you mean by W here. Right.
Yeah, you could have, because here it's just white noise.
Yeah.
Okay, here, in each location you have
motion.
just something which is
Yeah,
a right motion, but you could
Yeah.
put something.
But then what do you do? How do you take expectations and all this?
What?
How do you compute expectations if you have some kind of weird noise? You need to work a lot more in stochastic analysis. But yeah, I mean, you can choose. Yeah,
No, it
whatever.
would be. Would it be more difficult? I think it's easier, no?
But the cool thing with bundle motion is you can do all the Ito-Stratonovich calculus very easily.
Yeah.
But if you change this, then you need to work in. I don't know. Yeah. I mean, if you change this, what do you mean by Fokker-Planck?
But practically, when you want to simulate the trajectory, what?
Yeah, practically, yeah, you can do. Practically, it's just I just take random numbers here usually. I do Euler-Hein methods or Euler method.
No, but you could have something which is which will. Oh yeah.
But the trick is you have noise in the queue, so in the queue here. So yeah, you always, depending on the what you mean by W, you get the same roughness of W. Yeah.
As a statistical model on the data set,
Mhm.
don't you have some identifiability issues in terms of you're saying the model is completely characterized by these sigma?
Yeah.
And then
I mean,
different values of sigma don't correspond to the same set of
exactly.
distributions.
Yeah. So the in principle the sigma are a function of your image. So you have infinite number of parameters you can choose, right? But there I just said I want sigma to look like I want sigma to be this. So I have flat number of parameters, but this is just a prior. You can choose something else. You can choose Fourier modes.
But you have
What do you
also
mean?
the law for the initial
Yeah.
direction, no?
Yeah.
Which is really important.
Yeah.
And the estimation, you assume that you know the initial direction? Because
Yeah, so it's
when you have a data set, usually you have a mixture of both.
Yeah.
And you have
No,
different
yeah.
direction and different.
So when you do
So
this,
usually
when you
it's a
minimize
mixture,
this,
so
yeah.
you cannot.
So what you do is actually if the noise is small, then the mean path doesn't depend on the noise much. So you can say, okay, let's just find P such that the mean trajectory is good, and then find sigma such that the variance is
But
good.
you
So you do it in 2 steps. Yeah. But yeah, you need to choose some good prior of sigma to be able to solve it, and this is up to you, right? It's like a prior on, yeah. So you need to come up with a good strat of sigma such that you can match closely and make sense what they mean in your data. So here would be something like in your image, you have more noise in this region of your image, more variability here, and less variability here, and something like this. You can take Fourier modes and have something more non-local. Yeah.
Any more questions? Stefan?
Just a comment that you can also take the initial condition simultaneously. You can estimate all parameters this way. Right?
Yeah, so Stefan, you can say that, yeah.
But also with, I mean, in Ciano you just take gradient and then pick your parameter and take gradient upwards.
Yeah, so you can do shooting with noise. You can have noisy paths. You fix the noise, and you want to match the final point, right? And you can find the initial momentum, which depends on the noise you choose. If you want. That's what you mean, or?
No, but
So
I
the
say when you
P0 is
estimate-
a
when
round
you-
variable.
Okay, if you have a data set, usually you can assume that in fact what you see, you have different things. You have different directions,
Mhm.
initial direction, and
Mhm.
okay, you have also all the parameters for the reliant noise you have, and so
So
usually you have to. You're not in a situation where you know you have not a data set where you say it corresponds to the same initial direction, but
Yeah,
it's
yeah,
just
yeah, yeah,
replication
yeah,
of a
yeah,
different independent sample
Yeah.
of noise.
Yeah, exactly. But so what I mean by this is a mean initial momentum. So each one of them has different initial momentum.
Yeah.
Exactly, but this is just a mean one. And you assume the mean, you need to assume, I didn't say it, you need to assume that the variance of the initial momentum is 0 or something. You can say it's not 0.
And so usually
Yeah.
what you see, you have
Exactly,
mixture.
so, yeah, I
So
forgot to say, that's a
I
good
see
point.
that
Yeah.
the estimation problem is more.
Yeah, it's a good point. So here I say
Other
PP, mean PP is 0 in this example. But if you have some prior on what mean PP 0 is,
Yeah.
it's better, yeah. No, exactly, yeah, sorry.
So, Alain, let me just mention, if you have very good data, lots of data from Atlas, you can make a correlation function, okay, between the various types of various images. And it's, the sigmas are the eigenvectors of the correlation tensor. Okay. So your data tells you what the sigmas are.
Good. Okay. Well, let's thank Alexis and all our speakers. Thanks.